It's terrific to see some familiar faces and some new friends to Aspen's programming here in New York City. Ever since we started doing some programming in New York, it's been extremely well received. It's continuing to expand, and the primary institution in which we love to do convenings like this is here at Hunter College, the Public Policy Institute. I don't see Jennifer Robb here at the moment, but want to thank her and Hunter for their generous support of this. And again, it's such a wonderful venue with its, not just its elegance, but its historic significance to be in the house of Eleanor and Franklin, and of course, Sarah Roosevelt. The program that we're here tonight part of is part of our series, Conversations with Great Leaders, in memory of Preston Robert Tisch. This is an extraordinary program, and we have the children of Preston Robert Tisch to thank for that, Lori Tisch in particular, Stephen Tisch, and Lizzie and Jonathan Tisch, and the Lori Tisch Illumination Fund. And it just goes from strength to strength, the variety of remarkable people we have here and the kinds of conversations, but all are the kinds of things that we think that Preston Robert Tisch would have enjoyed himself. A towering figure nationally, particularly in New York, in business, obviously in sports, in education, in philanthropy. And all of what we do is, we think, a very fitting memorial to his inspiration and his ideas about what great leaders could do to improve their communities. Tonight's speaker, Brian Greene, is probably one of the few physicists and mathematicians who really doesn't need an introduction. And I think that's really one of the remarkable things about Brian, an enormously distinguished scientist in his own right. There are very few people who have done more to explain science than he has, and explain it in compelling ways without simplifying to the point where it's no longer accurate, and doing so with passion. And at a time when we have so fewer young people engaging in science than we need, it's extraordinarily valuable to have someone with Brian's gifts speaking as eloquently as he does about science. He's written at least 3 fabulous books, 2 of which have have moved on to television. And he's also a very good friend of the Aspen Institute, comes to Aspen frequently. And for those of you who will be coming to the Aspen Ideas Festival this summer, you'll have a chance to see Brian there. He's also here in New York, of course, the co-founder of the World Science Festival. You'll no doubt hear a lot more about Brian and his work in the conversation that we're about to have, which is going to be moderated by Robert Krulwich, again, someone I think probably all of you know, the science correspondent for NPR, a very familiar figure on radio, in his blog, and he too is someone who has a gift for explaining complex scientific principles in ways everyone can understand, even using drawings, cartoons, videos, and the like. He also has a nationally distributed radio and podcast series called Radio Lab. And I think many of us probably remember him from his many years as a correspondent for ABC and CBS News, not just in science, but really across the spectrum of topics. So I think we're in for a very exciting conversation, and I now turn it over to you.
Thank you. I guess we should confess at the beginning that Brian lives around the corner from me. And so we sometimes just wander back and forth. So we are familiar. Therefore I thought I could just ask you stuff. For example, it's always been curious to me because, scientists have always been a bit of a mystery for people who aren't scientists, particularly good scientists. When did you know that, because you can write, you can act actually, and you have acted, so you had other options. So I'm just curious, like, what happened? Was it one morning when something happened to you? Or was it a slow slide? When did you say, I think I'll be a scientist?
I think there really was one particular moment. I mean, there were things that happened before, no doubt. But I grew up a little bit further away from you than I live now on 81st Street between Columbus and Central Park, which in those days was a very different kind of neighborhood than it is now. And I remember my mother would always, whenever it was raining or wanted to get me out of her hair, would send me across the street to the Hayden Planetarium. And so I'd spend a lot of time there wandering the very dark halls. It was a dark place in the old days.
Did you like weigh yourself?
Yeah, that's right. They had all the scales with Mars and so on. But now it's very bright and airy. It's very dark, but it was just great.
Yeah.
And I remember leaving there one day. I was like, I don't know, 12 or 13, and I got kind of gripped by this sense that I think all of us get at some point or another, which is the question of, we're so tiny, right? I mean, what are we here for? You know, what is this crazy place where we find ourselves? And the next thought that occurred to me was, clearly there can't be an answer because I haven't heard it. So people must have been thinking about these things for a long time, and if there isn't an agreed upon answer that's out there, there probably isn't one. So don't try to find the answer, but maybe I can help to understand the questions a little bit better. Not,
wait, the thing that was tickling you was, why are we here, or how?
Well, good. That's exactly the point. So it was certainly the why. It was exactly the why. But
no,
forget about that.
I don't think that's going to get you to be a scientist. The why are we here?
Well, good. Then I said, you know, maybe I should have been a philosopher, but I gave up really quickly and decided to go to the easier question: how did we get here? Because it felt to me like at least that's one where you might make some progress. You might be able to get some sense of the mechanism of how we got here, even if the question of meaning would be beyond anything that we could reach. So that drove me to physics, because that is a subject which really tries to grapple at least some parts of physics.
So it was like 3 in the afternoon on May 3rd, 1976?
Yes, I didn't keep a diary, but yes, there is a date where I had that thought. But look, I mean, that's a little bit, you know, misleading. I as a little kid, I was fascinated by numbers. Totally fascinated by numbers.
I suspect that all scientists have this, I would call, problem, which is if you went up to a kid and you said, okay, I'm going to ask you a question. Should a poor man steal a loaf of bread for his hungry child? Or how much acceleration do you think it would take to take that 20-ton object and put it in the air? That some kids will say, I'll do the tonnage thing, and some kids say, I'll ponder your poor father question.
Yeah.
So you fell into the tonnage. You wanted to answer a question which there might be a clear answer to.
Yeah, no, that definitely was thrilling to me, that there were a set of interesting questions for which there was a definite answer, and it didn't actually matter how you got to that answer. There are many different ways to get at the answer, but if you were doing it logically, sensibly, the pieces were interlocking, it wouldn't matter how you got there. It would be the same answer. And there was something deeply thrilling about that fact.
Now, there's something deeply thrilling about being William Shakespeare, too. So he goes to work every day, and he makes up something, and the play that he makes this month is going to be utterly different from the play he makes next month, utterly different from next. So that's a life of variety.
Right.
A scientist goes to work and looks for patterns, like, that's happening, happening again, happening again, happening again, happening again, happening. So I'm just thinking, the thrill of this is sometimes lost on some of us.
Yeah.
That you are counting a lot, and you hope that the count will be very regular.
That's sort of true.
Yeah.
But it sort of misses the bigger picture, which is, it is all about finding pattern and regularity, but what's exciting about it is not that the same thing happens if you do the same thing, but rather the same kind of principle governs a whole variety of different physical phenomenon, and that's the constant. It's taking the complexity of all that's out there, the things that look as though they are completely different, not the same, and seeing that behind it all is this regularity, this idea that governs it all. So it's reducing the complexity to the simple by virtue of going deeper than appearances.
Is that just intellectually fun, or is it the fact that it's useful good? Like, if I build a plane and then put it in an airport, and you can get on it, and even though it's extraordinarily heavy and doesn't look like it could ever be in the sky, it just gets in the sky because some smart person has figured out how to do that. So that's to make a plane, to figure out why the plane would fly and to get it, that's useful. Also, there's no Tinkerbell required. There's no clapping and poking and little dust. You know, that's the other way to fly, the Peter Pan way.
Gotcha. I didn't know where you're going.
Well, miracle, yeah. So I'm thinking that you like a regular universe, which is a useful universe.
You know, it's a funny thing, because the useful side of it is really what the engineers do. And the engineers are great people, but they are, I think, driven more by finding the utility in some of these ideas. Much of what I have spent my life thinking about is not particularly useful in that sense. It doesn't change anyone's life. It doesn't put any new gadget in our hands. It doesn't put additional food on the table. It doesn't do any of those things, at least not yet. Who knows in the far future. So the driver really is not the usefulness of it. The driver is touching something that might be eternal, touching something that goes beyond the ephemeral experience of everyday life and reaching into the laws that might be the laws that are always there and always have been and always will be.
But you know, it's driven to some degree. Like, I guess if you're Shakespeare and you think up Hamlet, that's yours. No one can argue with it. Like, if you weren't there wouldn't be any Hamlet, Mr. Shakespeare. If you're Newton, what happened really was you just got there first. You found, so what is the vanity of this?
Well, it is in some...
Because someone else might have discovered gravity if Newton hadn't. I mean, I presume.
Yeah, all that is completely true. And in many places in the history of science, in fact, there were separate people who were developing the same ideas in parallel. So Newton is actually a good example, because he was inventing the calculus while Leibniz was too, and there are actually arguments that ensue as to who should get the credit. The vanity issue does come up frequently, but there is a certain kind of thrill that's hard to get any other way when you are the first person to see something, to see through the veils that are obscuring the true nature of what's out there, and you sit there for a moment and say, I'm the only person who knows this. I'm the first person to see this.
Have you ever had that? Have you ever thought?
I have had that experience, rarely, unfortunately, and because they don't happen often, at least in the career of mortals. There are others like Einstein, who are different. But so
But do you know? Like, let's suppose you've done an equation, and the equation has led you around a corner, then around a block, and now you're up for you think you're the very first one to stand at this particular logical point. Do you think first, I better go back to the library to see if some guy in Japan hasn't already been to this corner? Or do you think, I know the breeze is fresh on my cheek. I am Magellan for this one moment.
Well, the work that we are doing is typically so new that you know the players and you know what's been done, and there really is no chance that there's some dusty book in the library that might have the thing that you thought was new.
So you're Magellan, and in the harbor you can see Pizarro not getting there.
Oh, totally, because the very ideas that you're using are themselves so new that they aren't in any books yet. So there is no real chance of that being possible. But yeah, there was work that I did on showing that space can rip apart. So Einstein had a great insight, which that space could stretch and warp and bend, and that's his general theory of relativity, and it is a powerful description of how the force of gravity works. But in his theory, space can bend and warp, but it could not actually rip apart. So a question that we asked ourselves was, in string theory, which I work on, which is a theory that goes beyond Einstein's in some ways, would it be possible for space to tear in that context? And we worked on this for months and months on end. In fact, it was at the Institute for Advanced Study where Einstein had been, so there was a certain kind of appeal to working on a question like that there. And we reduced it to a calculation that we could put into a computer, and we did it, and the result popped out, and it turned out that if the number that popped out was 12, space could tear. And at first it popped out 3.999, which was distressing to us because it seemed like it couldn't tear. But then we said 3.99, it's close to 4. Maybe we dropped a factor of 3. You know, we went to the blackboard, we found that factor of 3, put it back into the computer, and indeed it popped out. And at that moment, we were looking at something that really had not been found before. And it did have that sense.
Well, that's such a weird thing, because you look at the math, and the math said, according to me, a total abstraction on a blackboard, space will tear. You hear no ripping sound. Space stays exactly where it always was.
Yeah.
So what you've just discovered is an idea, right? Do you think
Yes.
that the idea is the same thing as the real world that exists around?
Well, and that's, you can ask that question doubly strongly because we were working in the context of a theory itself, which we don't know if it is relevant to the real world, which is this approach of string theory. So within this hypothetical theory, we were finding that the mathematics allowed for a certain kind of process to happen that within Einstein's theory could not happen. Now, does that mean that it happens in the real world? Well, you have to assure yourself that string theory describes our universe, a question that we still don't know the answer to. And then, if that's the case, it's not necessarily true that everything that can happen does happen.
See, that's the hard part. In your field, like if I were Galileo, I think, well, maybe I'm going to go to the top of those towers, drop some balls, which I may or may not have actually done, and then I'll see whether a heavy ball and a ping pong ball get to the ground at the same time. I can actually think it up and then do it. You think up something that might be possible, it certainly looks like it that way in the math, if the theory that surrounds it is possible, which you don't even know, and then you turn around looking for an experiment to do, and there is none, so you have to sit there in your pajamas for the rest of your life, wondering whether what you did was true.
That's right. Things have gotten hard in the last 400 years. You know, there was a time when physics was about things that you could directly touch and feel. And obviously, physicists began with those kinds of questions because they hadn't been sorted out yet. You know, you take this cup, you drop it to the floor, what happens? And Isaac Newton did a really good job of answering that, so nobody tries to work on that question
Well,
any
Einstein
longer.
said wrong, right? So,
Good. So any insight into the world typically has limitations on its range of applicability. And that's a great thing. So when it comes to cups falling to the ground, you really can say that Newton basically got it right. Even Einstein's insights won't change that in any really measurable way, at least with technology that we can get our hands on. But you're right. Einstein then went further and said, what if you drop this glass not near the Earth but near a black hole, in essence? What would happen there? And Newton's ideas would not give you the right answer, and Einstein's ideas would. So as science progresses, the range of applicability of our ideas grows larger and larger as we go from Newton's ideas to Einstein's ideas, which embrace Newton and go further, to the quantum ideas, which actually allow us to stretch the range of applicability in a different direction, into the microscopic realm.
yeah, but I'm afraid, like for the Bronx science kids in the room, I mean, I don't know whether you guys are going to looking forward to a life where you think of something, you do it in the math, it checks out math-wise, you can't test it for I don't know how long, and then when you have, it could be wrong if someone, even as smart as Newton, gets turned upside down by Einstein. Then, as right as you are for your 15 minutes, you might turn out to be wrong. So maybe you should become a plumber, where you fix the plumbing, and you know, it's a good day.
Well, you can do plumbing as a hobby, right, at the side, and then you feel like you've got something done. But, you know, I think science has such a range of different kinds of problems you can study. The things that I study are at that edge or beyond the edge of where we can test it, simply because the experimenters aren't smart enough. They haven't built sufficiently powerful equipment. They haven't found ways that we could access the world on incredibly tiny scales or incredibly huge energies. But there are other areas of physics, condensed matter physics, astronomy, astrophysics, cosmology, observational studies. There are wonderful things in neuroscience. There are things in nanoscience. You can get your hands dirty if you want to.
Okay.
I've chosen not to, and various other people as well. But it really is a question of what excites you.
Well, here's the thing, another suspicion I have of what excites you. So during the Higgs boson thing, so for some reason, we've gone this far and never understood why anything has mass. So I don't even understand why we wouldn't know that. Like, I know that this has some kind of weight, and I can't believe that you guys haven't explained why. So you have this big, huge theory, and say, okay, here's, we think, what explains why you can, this has, I don't want to say weight, but just mass. So I see you rooting for an idea which the math predicts, and you wanted to. Now, here's something, when I was thinking of coming here, I was looking for people who are just different than you. Do you know a person named Maria
Spiropoulos?
Yeah.
No, I don't. Who is that?
Okay, Maria. So she's at Caltech, and she's she's there with all those people rooting for the. Think about this. It's like a pack of the smartest people in the world saying, "Okay, little thing, I hope you show up. We're going to smash some stuff together, and there's going to be some garbage, and we'll look at the garbage, and we're going to see whether that little thing that we all hope for is there." All of us except Maria Spiropoulos, who says, "I personally do not want this particle to be a standard model anything. I don't want it to be simple. I don't want it to be symmetric. I don't even want it to be as predicted. You know what I want?" says Maria Spiropoulos. "All I want is to have been dealt a complex hand." So she was sitting there saying, "Surprise me, universe." But you guys are saying, "Don't surprise us. Let us see what we hoped, planned, and
now,
our minds."
But what makes you say that? What makes you think that we would?
Well,
say
because
that?
there's like a Pac-Man. I mean, I'm not criticizing because, of course, a lot of people for a long time have put a lot of thought into this. So they imagined the world should operate a certain way, and now they're waiting for some tangible evidence that it's that way.
Yeah, but
there's this
but that's not
Maria
right.
girl. She seems to
That's
think, whoopee.
No, that's not right. So we did have. So first of all, I should say, just because this is being streamed and it's going to be broadcast on Aspen's site, none of this affects describing the mass of a real object like a glass. That's a separate subject we could talk about.
Okay.
But it has to do with the mass of the fundamental particle.
This is what he does when I'm completely wrong about something. He says, "Well, that's a very interesting thought." He says, it's like a decorator who says, "That's a nice look," meaning you cannot buy that blanket.
But putting that to the side, the question of whether this Higgs particle exists,
Yes.
which, as you do say, has been within our mathematical theories for 40 years. It came from an idea of Peter Higgs and a number of other scientists back in the 60s, and it has been so thoroughly accepted even before it was discovered that many people, including me when I was a student and learned about this idea, I didn't know that it was hypothetical. It was taught as if it were true, and it was later on that I realized that it hadn't yet been proven. Mm-hmm. So there was a sense of inevitability associated with this particle being found as it was found and as announced on July 4th last year. But if you ask me and many other in the community, do you want it to be found? Or would you rather that actually it's not found? The dominant response would have been from, I think, many of my colleagues, we hope that it's not found.
Really?
We live for the moment when the rug is pulled out from under us and reality is flipped upside down relative to what we thought, because that's the big opportunity. That's the opportunity to go to the blackboard and completely change our understanding of things. When it all just falls into line as the theory predicts, yes, there's something gratifying about that, but it's not as exciting as having everything not work as you would have thought. Now, Peter Higgs feels differently.
I don't believe what you just said. I believe that you all go to work over weeks and months and years, and you build a model.
But why don't you believe what I just said?
Because I'll tell you why. Because you go and you build this model. I trust you, but I don't trust you.
Actually, I wrote about this in the New York Times op-ed. And not that you should believe an op-ed. No, but I'm trying to say this is not an answer I'm giving to you now. This is an answer that I've really thought through and had conversations with colleagues on over many, many years. And the reason I wrote about this was because, A, if it wasn't found, I wanted to be clear that that is not a failure, that's science. Right. You come forward with ideas, you look for them, and if they're confirmed, fantastic, but if they're not confirmed, fantastic too, because that points you in the next direction. And in fact, we're going to face this as a real issue coming forward because, yes, the Higgs particle has been found. But what if we don't find anything else at the Large Hadron Collider, this $10 billion machine, and all it finds is what you expected? What do you do then? Well, for us, that'll be a strong argument to build the next machine so we can push the frontier further. But let me ask you, imagine going in front of some congressional committee and saying, well, we didn't find anything interesting than what we thought, so we need another $10 billion to go the next step of the way. It'll be far less compelling than saying, look, we have this hint of this spectacular new domain from the data. It's not working. There's an anomaly. We have to go forward to understand that. That's a compelling argument, at least on its surface. But the other argument of not finding anything and that being a clue to what's happening next is a strong argument too.
All right, well, now that I've heard the whole thing, I'll just tell you why I'm suspicious of this. Because I think you all gathered there and had this thing that you were all expecting to see not been there, if you say that most of you would have come and say, wonderful, now we can go back to the drawing boards and begin all over again, that essentially means that docs, postdocs, whole careers have been washed into the sea at that moment.
No, those are the people that are old by that point. Seriously, these ideas have been around since the 60s. No, the graduate students and the postdocs, how do they make their mark? They can't make their mark if everything is falling into place. And I got to tell you, this is real. There are postdocs of mine and others who are leaving the field. Why? It's not obvious that there's anything new that's going to happen in the next 3, 5, 10, 15 years. So it could be that we don't have any revolutionary ideas or any really striking inconsistencies that need insight to resolve. So if you ask those young, hungry physicists, what would you rather have happen? That the ideas that your elders came up with are confirmed and you've got nothing to do? Or some anomaly happens that you have a chance to explain and change everything? What do you think they would say?
I think you're right. I think the younger ones would get all excited and say, okay, we can reinvent the world. Although there is something. See, the problem is that if I were at the racetrack and me and all my buddies had bet on, on Diggamaroo, and Diggamaroo was 2-1 favorite, and we all bet on Diggamaroo, and Diggamaroo fades on the last turn, and Shigaboo beats Diggamaroo, then yes, maybe the young, weird bettors would say, Shigamaroo, life begins, but there'll be an awful lot of pain in the room, which you're pretending to ignore.
Yeah, I think the mistake that you're making is that physicists, not all, I mean, there's a whole range of personalities, of course, but physicists, by and large, are not wedded to a certain idea of how the world works. They're wedded to revealing how the world works, regardless of what that description happens to be. So it's not as though, I mean, why don't you take string theory? I've been working on string theory since I was 23 years old. That's 27 years I've been working on this theory, and I don't know if it's right or it's wrong. So you would think, based on your reasoning, that I am rooting for string theory, I know it's going to be right, and if it is proved wrong, I will be crushed. And I got to tell you, that's completely wrong. If string theory is proved incorrect tomorrow, I would be thrilled. Why? I don't care about the particular theory. I want to be able to think that I'm pushing the boundary toward a deeper understanding. And if an idea is proved wrong, that is progress, because I won't work on it any longer. I'll focus my attention on other ideas to go forward. At the moment, I think it is the best way to put gravity and quantum mechanics together, as many people do, and that's why we have confidence that it's worthwhile to work on the theory. But I'm not a believer in the theory. I don't believe in anything until there's data that supports it.
All right, let me see if I can trap you into a corner where you do believe.
Now, have you ever been able to do that?
Not yet, but I keep trying time and time again. Mathematics. You are not only a professor of physics, you're a professor of math. And you seem to believe that mathematics is a kind of mirror of what actually goes on in the world, at least some of the time. I'm wondering, how mathematical do you think the real universe is? For example, Bishop Berkeley in the 18th century thought maybe everything we see about us, everything we know or think we know, is a construct of our minds. He thought it was all mental. Do you think that there's a universe out there, or do you think that the universe is in here?
Well, I think it's useful to imagine that there is a universe out there. Without that, it's very hard to do physics if you think it's all just happening inside your head. But of course, if you ask me how would I establish that fact, it's a very difficult question, because anything that I ever experience, as I think is the case for you, but I can't really know, does take place inside this gray, sloppy thing inside my mind. So, as has been revealed hundreds of years ago by philosophers, it's very hard to establish that there is a real world out there. So I basically say that's an interesting point, but I'm not going to worry about it any longer, because it will prevent me from doing anything that I find useful toward finding some deep truths. But it could all be on a house of cards, absolutely.
Do you think, because on a couple of our discussions we've talked about free will, and it's been a little bit surprising to me that I mean, I think that there are some experiences. Scientists measure things, and you know, they kind of have to. They have to do something they all agree on. I think, of course, we all probably do that. There's some experiences that you just can't measure. We could go up into a Vermeer over at the Frick, and I could look at it, and you could look at it, and we could go, oh, but we can't measure our ohs at all. Unless you think, well, that's what. See, I wondered about like how far would you go? Like, do you think that an ecstasy at a Grateful Dead concert, like someone just swooning over Garcia, would one day be a quantifiable experience? Like maybe you could look at the person's brain and say, well, we know, just bring me the brain, and you look and go, yes, this is a person presumably now experiencing a Grateful Dead concert. This is the Grateful Dead pattern in a human brain, and be right.
Oh, absolutely. I don't have any doubt about that. I mean,
don't have any doubt about that.
The only issue there is it might be that the brain doesn't have enough distinct configurations to capture all distinct possible experiences. So the dictionary that you imagine between brain like this, experience like that, it might not be a one-to-one map. It might be a many-to-one map, so you may not be able to
just don't have a powerful enough computer to do it.
It may be that many experiences yield the same fundamental reaction. Because
see, now this is one of those things that drives me nuts. Do you believe that when you are given a choice between vanilla and chocolate by a waiter at a restaurant, and you look at the vanilla and you look at the chocolate, you choose chocolate? Do you believe that that choice of chocolate has been written down before you chose it, and that the future has already been written?
Metaphorically, yes. I don't think anyone has written it down. But if you're asking me whether I actually had the freedom to make that choice, obviously that's your question, right?
That's my question.
If I had free will.
This is what I did.
No, I don't think I did at all. At least with my current understanding of how physics works. So and I had no choice in saying what I just said either, by exactly the same reasoning. And you knew that, so this is all very circular at some level.
All right, now I'm going to quote Dostoevsky at you, because that's the person I should quote at you. When people say things like Brian Greene just said, he wrote, a man is not a piano key. And even more than that, even if it were proved to him mathematically or by natural scientists, he would still not come to what you would call reason. He would still do something contrary on purpose out of ingratitude alone, essentially to have his own way. We will have our freedom at any cost. I cannot bear the thought that I am simply a piano key, thinking and doing what I must when I'm struck. I want some kind of unpredictability in my behavior. I want freedom. Doesn't this resonate with you?
Well, first of all, he had no choice in writing that either, so I understand where you're coming from. But, you know, it's an interesting question, because he's talking about unpredictability, and he's equating that with freedom.
Yeah, but we all do that.
No, that's plain absolutely wrong.
No, it isn't.
What kind of freedom do you have? If your behavior was governed by a throw of the dice that I'm doing over here, so whatever it came up would dictate how you behave, but it was random, would that unpredictability feel like free will to you? You wouldn't be making any choices at all. It would be governed totally by the outcome. The outcome is random. So how could randomness and free will be the same thing?
Well, I wouldn't believe in the dice thrower. I just believe in me. I believe that I am commanding.
No. I make this point for a real reason.
Oh.
Because some people say that in quantum mechanics, you can't predict the outcome of any given experiment, there is a level of randomness that happens. You only predict the probability of getting one outcome or another. Some people say, that's where free will is. It's the randomness in quantum mechanics. And the answer to that is, that is silly. It's silly for the exact same reason that you didn't buy that you would have free will if I was throwing dice.
I never said this quantum
You buy
mechanics
free will.
thing. I just
Good.
said
That was my reason for saying it.
Oh.
But if you don't feel that way, that's good. But the point is, when you equate unpredictability with free will, that is dangerous. That's going down a path which is, I think, indefensible. But I understand.
What do you mean
But I understand
indefensible?
where it's coming from, because this is before quantum mechanics and all that stuff.
Yeah.
So the question
I
is,
don't understand how you could even think of a free will without imagining that I can freely choose between chocolate or vanilla. If I choose chocolate and it's my choice and I...
Good. I agree with that definition of
Okay,
free
so
will.
the fact that there might be a
yeah.
random...
But so the question is, do you have that level of free will? And I think you have to be a little bit more nuanced about it. I think the way to think about free will is the sensation of making that choice. And that's all that you have. And I agree that you have that sensation, I think, because I certainly have that sensation too.
Well, you
But
must have
the
a more
sensa-
complicated version of it.
Why, 'cause
you
I'm
say,
vegan or what?
waiter, no, because you're a vegan. Waiter, yeah, you can't order the vanilla ice cream. Waiter, I'll have the tofu version of the vanilla. But you knew that, or somebody knew that, or I knew. See, that's the complicated part. You have a
The
little
sensation
asterisk.
is enough. The sensation of free will is enough. And I then, like most other people, internalize that in an illusory way to make it feel as though I really made the volitional choice of whether to pick up this glass or not, when fundamentally I don't think that I did, but the sensation is enough. It's enough for me to be invested in what happens in the world around me. And therefore I don't
know
sit back
how
and
you
say,
get up in the
I've
morning."
got no, well, that's my point. I don't sit back and say, it doesn't matter, it's all determined anyway, I'll just lie here in bed. I'm invested in what happens because that sensation is real, it feels real, and it's enough to keep me buying into the illusion. And that, presumably, is an evolutionary advantage, and that's why we feel that way.
You go through all of that? I just get up because I think, Robert, I am getting up. And I say yes to myself, and I am captain of my own body and ship. You get up thinking, Brian, I am totally deluded here. I am going to pretend that it's my choice to get up, but I know underneath my choice is not a choice at all, but my getting up has been forced.
That's right. It's a question of, do you take the red pill or do you take the blue pill? Okay? And I choose the pill of truth.
Well, do you choose the pill of truth all the time? Like, do you believe?
No.
Do you believe that when you run faster than me for a bus, that time is just a teeny bit slower for you than me?
In the way that you're describing it, yes. I do believe that time elapses at a different rate for me than it does
I mean,
for you.
you palpably. Yes. I mean, I know.
Yes,
that
yes,
you think running to the bus. You think, look at me. I got to get onto that bus. And by the way, my time is passing slower than that boy sitting there on the bench.
Absolutely. Now, do I think that every time?
Well,
it would
no,
be a
of course.
little distracting after a while.
No, but I guess. But I'm
yes.
wondering whether, like, because there's so many. The reason why science is such a hard thing for many, many people to buy into is because it's becoming more and more and more intellectual and less sensual. Like at a certain point, it's just hard to believe that we're actually spinning on the Earth. I mean, everybody knows because we've been told for so long that we are, but our hair doesn't blow. If you throw up a ball in the air, it seems to land where it doesn't like go over your head and land somewhere backwards because you've spun with it. So it just doesn't make any sensual sense. And yet I think from the third grade on, we kind of understand that it's happening anyway. And then later on, you fill in and you say, well, the air isn't moving, it's sticking to the earth, so you're moving with the air and all this stuff. But it's largely an apology for something you don't understand. Your mind apologizes to you and say, well, I'm sorry, I know it doesn't feel this way, but we are spinning. I know it doesn't this, but we are doing this. I know it isn't this, I know it. But you seem to have achieved, while you're screwed up getting up in the morning, you have achieved a kind of happy certainty about these very intellectual propositions. You actually, I think,
Well,
I mean, this is what I believe you, because I've seen you not exactly running for the bus, but I think you running for the bus is the person who actually can think he's moving, the time is moving more slowly during that interval.
Yes. So I
That's
think,
so
but I think the problem is, and part of what I guess the title of this discussion was, it's about education or science literacy. And I think the problem is scientists have not done a good job of convincing people that these insights that feel abstract and separate from everyday life are very real, really matter, and give us a deeper understanding of how the world works. And I believe that if you had a teacher since the first grade who was really priming you on issues, say, of time and relativity, which you can begin to think about at a young age, it'd be far more intuitive than later in life trying to take on these ideas that seem strange and counterintuitive.
Is it intuitive like skating or riding a bicycle?
No, it's different. It's very hard because when you ride a bike, you have feedback from the bike. You really are taking in from a physical experience what it means to ride a bike. And unfortunately, we just can't travel near the speed of light. If we could travel near the speed of light, then the answer would be yes. Because every time you got on your scooter and went at 669 million miles an hour, when you came back after that round-trip journey, you'd look at everybody else and you'd say, wow, you guys have really aged a lot. And like, yeah, you were going fast, it's time for you to slow down. So you'd experience it. It'd be absolutely intuitive, and you wouldn't question it.
But you've swallowed the Kool-Aid here, and you believe Einsteinian physics just deep. Like, is there anything that we all know is true up here that you don't believe in here? Anything? So there's something you just never, that you remember. Like when I was in law school, for example, we had to learn this rule against perpetuities. I could keep it in my head for exactly 3 minutes, and if I ever tilted to the left or the right, it would fall out of my ears. I just couldn't, I not only didn't, it was just too hard. I was wondering, like, for a physicist, there's something that you just you have to keep coaching yourself?
Well, all the time. Because, again, these ideas are strange. Take quantum mechanics, right? I mean, the idea that something can pass through a solid surface, quantum tunneling, completely unintuitive because we never experience it, but experiments and the theory shows that it can and does happen. The fact that we talk about a world that's governed by probabilities when the world seems, by any everyday experience, to be definite. What does it mean for there to be a chance that that cup is somewhere else? It's right there, isn't it? So those sort of disparities, disjunctures between experience and knowledge, you navigate all the time when you're in this realm.
But I'm asking,
but you learn to mistrust your experiences.
That's very hard for people. But in order to really understand science these days, you can't trust your tongue, you can't trust your eyes, you can't trust your ears, you can't trust your sense.
But that makes it thrilling. Right? I mean,
let me ask you. If I were to walk through this wall,
yes,
just white, because I am mostly empty space, that wall is mostly empty space, so it just happens that I just do it the right way, and through the wall I go. These people would be shocked. Miracles would be, people would fall to their knees. But would you think, oh?
It happened.
I mean, are you that into this that you wouldn't be like...
Knowing that something can happen with some probability, which is what quantum theory tells us, and knowing I could calculate the odds of that happening, and it's a very fantastically small number. What does a small...
I will actually tell you, I have to go to magic
finish.
Shows with him, and there's like Ricky Jay, a great magician, is on the stage, and he's sitting there doing this math, and well, I'm going to go to 15 thing. It's 16, well, he can do that. And I'm thinking, can't you just watch the magic show?
That's true, I do remember that. But the fact that the calculation that I do revealed that the probability for that to happen is fantastically small means that if I see it happen, I should be surprised. You should be surprised if very unlikely things happen. You shouldn't say, oh, physics is wrong, we don't understand the world, there are dragons and there are ghosts and fairies. You don't go into la-la land, but you say, wow, something very unlikely but possible just happened. Oh, I should be surprised, and I am.
You almost said, holy cow, but you didn't say holy. What would happen if, instead of me walking through the wall, what would happen if a beam of light came crashing through this window and an angel called Gabriel descended and gave me a kiss like in Angels of America? If that was called Angel, to the Tony Kushner play. So I was lifted up by a traditional angel. Do you ever believe in miracles? Ever?
Yeah,
miracles.
I mean, no, look, if
not the miracle of life. I mean, miracles.
No, I mean, if the ceiling parted and a being was out there and said, "Hi, I'm God," I'd say, "Wow, that's cool." Now we know. And yes, it would change my view of things. It's not like I'm stuck on the equations of physics and everything that I see contrary to what I anticipate will nevertheless not affect my belief in those equations. I assure you that if the ceiling opens and God says, "How are you doing?" I will believe that there's a being up there that seems to contradict everything that I thought I knew, and I will start to update my beliefs.
I like the way you say that. Okay, I'm going to update my beliefs, oh big one. So let me conclude because I think we have to do questions. When is this supposed to end? Like in 10 minutes, right? Yeah, okay. Have you ever had an ecstatic experience? Not a druggy one. I mean, it's an ecstatic experience. Maybe the math. What is a math ecstasy like?
Oof. You wouldn't understand.
I mean, is it like?
No, I can answer. I mean,
okay.
You know, when you're doing a calculation and all of the pieces look complex and forbidding, but yet somehow it all comes together and cancels out and yields some simple, beautiful result. There is something ecstatic about that. It all worked in an elegant and spectacularly tight, logical way, and that is an experience that is thrilling.
Is it like send chills up your? Does it make your dorsal hairs rise?
You know, it can. I mean, you know, Einstein himself, right? So he came up with the general theory of relativity, and in the quiet of his own home started to use that theory of gravity to calculate the motion of the planet Mercury, which there was a real puzzle about for a very long time because it's so-called perihelion precession. The orbits were not lining up each time. So people were thinking maybe there's another planet out there that we haven't seen called Vulcan that's pulling on it, and that's why the orbit is shifting. So he sits there with the math, does the calculation of the perihelion with this new theory of gravity differing from Newton's, and the result equals what people had found, the shift in the perihelion. And he said that for days after that, he had heart palpitations. That's how thrilling it was. So the answer is yes.
Okay, well that's a good thing to end on. Heart palpitations. Okay, questions? Yes.
This has been a very interesting chance to get to know you two individuals.
A little wilder than you were
I think you
thinking
could
it
hear
was
me,
gonna
but I said this has been a very good chance to get to know you two individuals, and this repartee is fun. But I'm a layman, and I'd like to learn a little bit about science, because you're supposed to be somebody that can explain serious science to ignorant people like me. So, can you, in 5 sentences or less, to explain the string theory?
Who's going to count?
5 sentences.
Yeah, so briefly, string theory is an attempt to answer a question that people have been asking for thousands of years, which is, what is stuff made of? Right? If I take this table, I cut it in half, keep on cutting it into ever smaller pieces, what's the finest uncuttable ingredient that I get to? Now, a long time ago, we learned that there are molecules that are then made up of atoms, and we learned that atoms are not the end of the story. They can be split into smaller particles, electrons that go around a blob called the nucleus, which itself has neutrons and protons. And inside those particles are smaller ones called quarks. It's like a sequence of Russian dolls. Every time you look in, there's something deeper to be found. But conventional theory and experiment stops with electrons, quarks, a few other exotic species of particles as the finest ingredients that the theory has and experiment has revealed. String theory says that is not right. It suggests, and I say suggests, it's not a proven theory, but the math suggests that there's at least one more layer to the story. Inside electrons, inside quarks, inside any of the other particles you may have heard of, there would be something else. Something else is a little filament, little string-like filament of energy. That's why we call it string theory. And this little string-like filament can vibrate in different patterns. If it vibrates in one pattern, it will look like an electron. vibrates in a different pattern, it will look like a quark. So all the particles are united under one idea. Everything comes from the different vibrational patterns of this hypothetical entity called the string. That's, in essence, what the theory is.
So you're made up of dancing strings. Do you feel that way? Does your sensual feeling of the...
But this is really very interesting. I have some few other people ask questions like that because I've heard about string theory for 30 years, I guess, and never understood it. And now in that 5 sentences, I got a feel for what it's all about.
Okay. I guess I should go to a rear. How about, yeah, in the back, yeah, that you, who are wondering whether it's you. It is you.
Yeah, I'd like to go back to this point about the Large Hadron Collider not finding something. So let's say that it doesn't find anything else. And the standard model is incredibly accurate in the domains of validity and applicability as an effective theory. General relativity covers the big stuff, semi-classical approximations in between. How do you ask, some public entity for large amounts of money for something like this? Like, at what point do scientists have to sit down and have like a real conversation about moral and ethical causes, like reasons for doing science?
Because you're wondering whether if you don't have something you can promise the taxpayers, whether you should ask them for money?
Well, I'm just trying to be able to sleep at night. I'm a scientist myself.
Okay.
Well, I think everybody at some level answers that question for themselves. But my personal view is that it's our responsibility as a civilization to continue to push the envelope of understanding. We have been given that charge by the ancient Greeks that started along this road, and we are simply the current people that have the capacity to move science to a deeper level of understanding. So I don't see the world as a zero-sum game. I don't see our new Large Hadron Collider, the International Linear Collider, whatever the heck it is, I don't see that as meaning that money won't go for other important purposes. I would simply say, if you want to think in those terms, have a few less bombs, have a smaller military, make a more peaceful world, and take all that money and use it for these other purposes. So I don't think you should pit things that have a humanitarian quality against pushing science forward. You got to look at the full picture and ask yourself, are we making best use of all of the resources? And in that context, what we are doing is what makes life worth living, and that makes it important.
That was pretty eloquent. Yes.
A number of years ago, I remembered reading about the Webb telescope and that it would take us to the far end of the universe. And I haven't heard anything recently, and I was wondering if you could sort of update me.
I don't know the status. There definitely were some issues where at some point the telescope was under possibly being cut. And whether that actually happened or not, I haven't followed in detail. I'm not an observational astronomer, but it's an important issue. I mean, we actually, we have this thing called the World Science Festival, and in 2010, we had a full-scale model of the Webb telescope down in Brooklyn Battery Park. And again, that's the kind of thing that got kids so excited about the possibilities of the things that one would find out there. But the realities of money and financing, coming from the previous question, have had an impact. And whether or not that telescope is still on the docket, I don't know.
It's still on the docket.
It is, good. What's the current timeline, do you know?
I think a couple of years, the cost overruns, it just got really, it got expensive. And
Is that
so,
Gabe back there?
That's me, yeah.
Hey, how you doing, man?
So other projects had to be cut in order, basically NASA decided to put all the eggs into James Webb.
I see. Thank
So
you.
it's happening, but it got really expensive.
Yep.
Mr. Blue Shirt.
Can you give us 5 sentences on the Higgs boson?
The Higgs boson.
Boson.
Yes, so a question, and this is what Robert was referring to, that we have struggled with for a long time is, we know that particles have heft, mass, And mass, you can think of the resistance an object offers when you try to change its speed, right? You try to push against a truck, it resists it. That's the mass of the truck pushing back against your hand. The question is, where does the mass of fundamental particles, like electrons and quarks, where does it come from? Why do they have any heft at all? And the answer that was put forward in the 60s that we have all bought into for a long time is this. Particles like electrons and quarks are moving through space, and space itself, the proposal goes, is filled with an invisible Higgs field, is what we call it. It's a molasses-like substance that fills space. And when particles try to move through this molasses-like substance, they feel a resistance. And when you try to push on them, it's that resistance that we feel as the mass of those particles. So it's a strange idea. In every nook and cranny of space, there is this invisible molasses-like substance, and that is responsible for giving particles their mass. How do you test this idea? Well, the proposal said, if you slam particles together, like protons, which happen at the Large Hadron Collider, slam them together at very, very high speeds, sometimes those collisions can jiggle this invisible substance and flick off a little speck. And that little speck would be a Higgs boson. So the idea is, build this big atom smash, or particle collider, the Large Hadron Collider, slam protons together, and see if you can see that little speck of the Higgs field flicked off, that Higgs particle. And that's what has now been found.
And that particle is smaller than a string? Or smaller than
If string theory is correct, then that particle too would be described as a string in a certain vibrational pattern. So if you want to talk about big and small, it's a concept that doesn't quite apply way down in the microwave, but roughly speaking, the string would be smaller. The string would be vibrating, creating that Higgs particle, that Higgs boson.
Tom, you.
I've been reading a book recently about, thank you, about time. And it's probably one of the things that confuses me most about theories, time, space. And this author proposes that time is either absolute, it's an illusion, or physics, it's an illusion. So my question is can you expound upon the idea of time as it relates to these theories?
Time is the big puzzle, and I would say it's a subject that we have been able to learn a lot about the characteristics of time that differ from what we would think based on experience. So starting with Einstein, and as we briefly discussed, we learned that time is not the same for all of us, doesn't tick off at the same rate. Very surprising. If you're moving, time ticks off at a different rate. If you're near a body that has a strong gravitational pull, even the Earth, time ticks off more slowly than it would if you're far away from that body. Totally unexpected, but yet we now know that these features are true. But if you go deeper than that and say, well, what is time? Where does it come from? Is it fundamental? Is it something that our brains make up? Is it deeply woven into the fabric of reality, or is it an emergent property that only happens in certain environments? Could there be realms out there where the whole notion of time doesn't even apply, doesn't mean anything? These are questions that we don't know the answer to. And the book that you're referring to, I presume it's Lee Smollen's book, is that the, yeah. You know, Lee has interesting ideas, highly, highly speculative ideas that come from his approach to unifying the laws of physics, and string theory has its approach to unifying the laws of physics. And the bottom line is, we're quite up in the air as to the deep understanding of time. And if you ask me, what will the next revolution in this kind of science be? I presume it will be finally coming to grips with what time and space actually are.
In his book, one of the weirder things you learn is that time doesn't have to just go forward. At very, very small scales, it could go either way, which is so deeply odd since you just rarely see your kids get younger. It just doesn't happen.
One question, and
One
then we're
more
going to
question?
have to...
Yeah, go ahead.
So I'm a high school physics teacher. I have some of my students here with me tonight. And, you know, I have a dilemma when listening to you describe some of the fascinating aspects of physics, and I'm thinking, oh, did I even mention that in my class? You know, and maybe I skirted on it for like, you know, half a day because, you know, I have them for 1 year, and probably it's the last physics class they're ever going to take. And of course, I spend my time with, you know, classic Newtonian physics, and we barely get to talk about quantum physics or any of, I guess, for lack of a better word, the sexy stuff in physics. But is there any way that you could think that we could incorporate some of these more exotic, even though they're mainstream in the sense they're physics, but they're, you know, if I'm trying to teach mechanics, they don't ever show up
Yeah.
in the teaching.
I think there are ways. I think ultimately, and we see it starting to happen, the whole educational system needs to be turned upside down. I think that the idea that there are many, 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 many high school teachers all across the country and the world all teaching the same subject to these students, as opposed to having some spectacular digital version where the students can get the material that they need from that, and then you can play the role of the guide to the universe, answering their questions, taking them on a quantum journey, taking them places which otherwise you wouldn't have time to do. Now that's sort of a utopian vision, because how are you going to get the kids to watch this thing and really do it? So there are a lot of issues involved, but I do think that with technology, we can make the educational system not only better, but so much more efficient, freeing you up to do things that otherwise, as you say, would be very difficult to do.
You know, we could obviously go on for hours. This has been so fascinating, and what a remarkable questioner. And just listening and eavesdropping on the two of you has been such a treat. But I wonder if I could just ask one last question, because of the comments about education and even the question about time. My sense, and it relates to the public mistrust of science in the United States now. My sense is that the public attitudes towards science are not particularly affected by Higgs boson or what happens when protons collide. It's still largely affected by what scientists say about things like evolution and climate change. And those are concepts that involve time over such enormous periods that are very difficult for human brains to appreciate. I just wonder if either of you have any observations about the fundamental reasons for what appears to be increasing mistrust of science, which has implications for funding even in the physical sciences.
I mean, I can just give a quick, and then maybe you want to finish. The one thing I will say is I understand exactly what you're saying, but you started by saying that you don't think public attitude is affected by such discoveries like the Higgs boson and so forth. I was amazed at the interest in the Higgs boson. It was actually enormously gratifying.
Enormously interesting, but it didn't lead to any negative repercussions in terms
No,
of...
but I think that's the point. I think that it really, for many people, did cast science in a different light. They were excited about what was happening. It was something that was deeply enriching our understanding of the world, and I was shocked.
But it didn't threaten people either.
But that's okay. Science doesn't need to threaten people. So yes, so I do think that fundamental discovery can really affect the way people think about science, as long as we get the ideas out there. And why did the Higgs and the LHC get out there at all? I'll tell you why. It was because in 2008 there was a thought that the LHC might produce little microscopic black holes. And people started to hear about this and got worried. I don't know if this was a PR ploy by the Large Hadron Collider, but it was brilliant, because in 2008 I got all these calls to be on, you know, ABC News and the NewsHour talking about the LHC, and I was like, wow, people are really interested. And no, that wasn't what it was about. They all wanted to know, is there going to be a little black hole? And at first people were like, well, a black hole swallow up Geneva, and, Europe, who cares? But then it was like, well, maybe it'll swallow up America. You know, then people started to get really worried. And so it did in some sense come from a threat. But ultimately, the fact that this machine was able to so deepen our understanding of the world, I think many people have found very, very impressive. But why don't you speak to the others if you want?
Well, for me, being on TV and on radio and on other stuff, I'm very aware of the mood that the audience is in. And on the one hand, it is true for Radiolab and the things I do, the audience is spectacularly large, surprisingly, and all over the world, generally kind of young, although getting older. But there is this other thing that's always out there, which is that there are people who think that the scientists should know stuff and say what they know, and there's some kind of power that they have, kind of a wizardry power, that they should tell us what we need to know, and they should know it. But they seem to keep changing their minds. And they say this, but then sun tanning on Monday, but then that makes you sick on Tuesday, and then it's good again on Wednesday. And they don't, they then think that there's something funny about these people, and that they're in it for some advantage, that they're manipulating us. And there's suddenly a distance growing, so there's a them and us kind of feeling. In some cultures, this very, very radically rational sense of things feels scary, because people do love miracles, and they love the comfort of routines that they've gotten used to, and they love their senses. They love what their mouths and their eyes and their ears tell them, and they don't want to be told that it isn't true. So there seems to be a robbery going on in some of these people's minds, that these people are taking things from us, probably for their own advantage. And it's spread from the United States to India and to Turkey and to even Japan. I mean, you see it now showing up in more and more places, this suspicion of the class of science. And to my way of thinking, the way to talk back to that is to tell stories. Brian is probably one of the great ones. He can tell stories, as you just saw. Like a person asked, like, what's string theory? Tell it to me in 5 sentences, and he almost did, plausibly. And that is a rare skill. It's almost a Spielbergian skill. So what you have going on culturally is you have a group of people who have stories to tell. You have Bible people who tell beautiful Bible stories. Movie people tell great movie stories. So you'll have cocktail waitresses being examined by extraterrestrials gorgeously, and it'll be and then you'll have TV shows and radio shows that tell the science stories. And I guess to me, I think the science stories are every bit as good as the movie stories and the Bible stories. Every bit as good. But the people who practice the science have to be a few more Brians and Neils and people who get out there and who just tell the stories vividly. But in a mano a mano, story for story, I don't think science has anything to apologize for. And I think that's where you do it, because people look for reassurance, familiarity, and for love. They want to fall in love with things. And these stories, the scientist stories, while we've been arguing about how unlovable they are, I mean, what I really know is that they're deeply lovable. And if you look at a robin on a lawn and you tell some kid, that's actually a modern dinosaur, and then you explain why you think that, that's a pretty cool story. You can't look at a robin ever again without thinking about it differently. But a lot of people who do this for a living don't know how to do that. Brian does, but not everybody.
Well, we're in your debt. We thank you very much.